is IPN-V, the Interplanetary Network Visualizer, being presented by our very own Juan Fraire.
Okay, yes, it's loading. Good. Excellent. Let me just move this away from here. Well, thank you, Ed, for the introduction. So I'm going to share with you a work that was mainly led by Alice Levihan here, our intern student at INSA Lyon in France. Yes, so and she was basically co-supervised between me, Pierre Francois, one of the professors that we work with at INSA Lyon, and also Felix Flange from ISA. Alice, she's currently an intern student now at ISA with Felix. So yes, we have been exchanging quite a lot about different ETN-related topics. But the first work that Alice was started to do with us has to do with the tool that I want to present to you today, which is the Interplanetary Network Visualizer, or IPN-V. Let me see if this works. Interesting. My slides are not moving. Okay. So, yeah, IPNs, right? So interplanetary networks, we care about this. We essentially, it's like kind of the definition for the backbone of communication between spacecraft and satellites on the interplanetary scale. We also know this as solar system internet as well, and we are talking about networks on an interplanetary scale. And of course, as we all know already, the main characteristics of the systems are severe delays, disruptions, and also very complicated and constrained operational conditions. And we basically work on DTN and similar related architectures to operate in such harsh conditions. And well, Van der protocols, for instance, is one of the main outcomes of the technology approaches for dealing with IPN and solar system internet in general. The main problem that we see on IPN actually that motivate this work is that actually the space and time magnitudes that we have in these systems are actually way beyond the intuition scope that we have on a day-to-day basis in terrestrial networks, at least, or even in near-Earth networks, like in Starlink or close to Earth constellations. And then this is even if difficult to explain or to show on a text or in a numerical way. And in my opinion, this is a significant gap in the community nowadays, because all of us are working on creating protocols for interplanetary scenarios that we don't really have a concrete or solid intuition on how they actually look like. And they're also time dynamic. So we notice that there's a significant gap in that context that basically makes that I've seen many papers and works working on far unrealistic interplanetary scenarios or overly simplistic or even incorrectly defined because of this lack of intuition, right? And this is, in my opinion, one of the gaps, as I mentioned. And there we have quite a weak understanding of the dynamics and the distance that are involved in these systems. And in consequence, this actually limits quite a lot, I guess, the effectiveness of the work we do as protocol designers, and also the impact that this can have, because we are unable to put forward, in many cases, how are these interplanetary scenarios really looking like in terms of distances and in terms of planetary positions and so on. So there are quite a bunch of tools around that we can consider for helping us in getting this intuition. Most of these tools have some visualization capabilities that we can use. So I would say that possibly STK is one of the most advanced in terms of features. STK is a quite sophisticated satellite and orbital propagation tool with a lot of plugins to do many things related to space design and operation. The issue about STK is mostly that it's licensed, and it's actually quite an expensive license. And this makes things quite complicated for researchers, for instance, really to access this tool, and also for small companies as well. So STK, I would say, is the state of the art, but at the same time, it's very limited in terms of how can we access this if we don't have like a big pocket. So there are a few alternatives around. I can mention like ESA's Godot is also very popular library for also propagating and making quite sophisticated mission analysis. I would say that also ORCID is in the same table there, but both of them actually lacks a concrete visualization support system that can help to again, I'm talking about getting intuition on how these networks actually looks like. NASA EYES is, in my opinion, is all the opposite. It's a fantastic tool. I mean, if you have not tried it online, I suggest you do so. You can have fantastic visualization of the different contacts that you have between Mars assets and orbiters. And they have like very fancy, let's say, visualization approach to actually show this. But it's a web-based interface from NASA. You don't get access to the source code. You cannot add like other spacecraft, or you can play with it in a free way. So it's definitely also quite limiting in that context. GMAT, I would say, is also another tool that I would like to mention. GMAT is a propagator tool developed by NASA, where you can run quite a lot of interplanetary calculations. It's an open source tool as well. And it also has a visualization to user interface, but it's quite limited. So, for instance, it's very difficult to navigate in time with GMAT. I mean, you can get a visualization idea of how the trajectories of the assets are, but then playing with time and moving back and forth with time is something you cannot do with GMAT, unfortunately. And also, GMAT has no support for visibility computations, right? So contact lens computation and so on, you cannot do that with GMAT nowadays. Cesium is possibly another tool that I can mention over here. It's quite popular. It's a web-based tool that I think is kind of a spin-off from SDK from the back in the days. And it's a JavaScript type of UI where you can also add some things there. But unfortunately, Cesium is focused only on Earth. And this is also the case of many other tools. And I basically bring this refer to this LinkedIn post that I saw some weeks ago about a guy saying, stop doing 3D tools for visualizing satellites. There are too many already. And actually, I mean, he made a very exhaustive list, which I liked a lot, about different UIs for satellite visualization. Many of them has to do with the RE type of visualization, right? To show the cloud of assets in LEO. But unfortunately, none of this is actually useful for us even, right? Because all of these are center focus on the Earth, right? So we don't have any way of extend them or use them in a way that we can actually use it on a solar system scale. So I would say that, again, like SDK is kind of the state of the art. And this is the type of visualization you get with SDK if you want to run on play with an interplanetary system. After some hackings with the Windows, because the max visualization range that SDK offers is limited, you need to configure that by hand. And after some time, you can get a good handle at it. And more or less, what you get as a result is, I mean, it's reasonable. You can see like the time evolved. This is the DSN with links to every planet on the solar system, plus some orbiters around there. So, I mean, it makes actually quite a nice job in general. Yes, but as we said before, the licensing access for SDK is actually quite limiting. So, this has been a question that's coming back, motivating me for quite a while already. And in 2022, IPN-V opened the question of, we need a video, we need a way, we need a material, we need to generate a material that can help to transmit to our associates what an IPN is. And we have people in IPN-V, by the way, IPN-V is a special interest group for interplanetary networking, that, I mean, we have associates from many parts of the world which are not experts in orbital dynamics or are not expert in space systems. And it's quite challenging to really convey the idea of what IPN is. So they say, yeah, we need to generate some material to actually convey this message to our people. They say, yes, let's make a video about which is our vision in the upcoming 100 years on how IPN will evolve. And we quote for a few professional video renders and models, and this is the number $30K USD for 1 minute video was kind of way out of the budget that we have at IPN-V. So with Kaneko, discussing with Kaneko, he said, well, let's open like a kind of a concourse or something that people can volunteer and apply to something. And the price was far humbler than the original cost from a professional video editor. So we started also, say, let's try and let's apply it and see if we can get something done. So I started with a program. We have an expert here in the room about Blender, so Lee can talk about Blender for hours, I guess. I tried to make something in Blender to visualize IPNs, and it was super difficult, honestly. I mean, it took so many time modeling things, and and so on. So we really need like a concrete background to make something happen concretely in Blender, which is an open source 3D modeling and rendering tool. So then I moved to Unity 3D and started to make some tries there, and that works out actually quite well. And I have a video to play following, which is the result of this 100-year video that actually we are using another IPN-SIG to present IPNs. Let me just try to also. There is a nice voiceover of Mike Snell here. This is kind of the result. Maybe it's a little laggy, I guess.
Connecting people across the globe to satellites aiming data from space. Humanity has always pushed the boundaries of communication.
So this is Unity 3D basically working there.
Thanks to the proliferation of satellite mega constellations. However, humankind's curiosity extends even further into deep space. Beyond NASA's Deep Space Network already provides point-to-point links with assets on and around Mars and other less permanent locations like comets and asteroids. However, in the not-too-distant future, we will launch even more deep space landers, probes, and satellites than ever before. Following the same path as the Internet, relay and multi-hub connectivity will connect surface nodes and satellites orbiting remote planets. Well-connected remote networks will increase our understanding of the solar system and create opportunities to unlock new discoveries. As the technologies required to conduct increasingly complex robotic and manned missions continues to evolve, the interplanetary networking infrastructure will be ready to support further exploration, scientific discoveries, and even commercialization of interplanetary space.
These are realistic orbital trajectories from realistic models. So the scale is actually to scale, right? It's really the real scale that you get.
Visit us to learn more and stay up to date on interplanetary networking developments.
And this video and this result came quite handy for us to showcase a bit about how does an IPN looks like, right? Otherwise, it's just a theory or a theoretical abstract thingy. So this worked out. We use also this preliminary prototype with Unity 3D for connecting with the HDTN guys here in Glen. We also to showcase some of the scenarios in a poster that was presented at InfoCon this year. But the prototype at this stage was a bit limited in terms of that all the planetary trajectory plus the satellite trajectory propagation was tightly coupled with the rendering and the visualization part of the tool. So this means that if you have like sophisticated topologies, then you pay with frame per second, essentially, right? Because everything was computed online. So we started to think that this is where I stop upon Alice and say, Alice, maybe this is when we can rethink a bit, and we need to decouple this out to have the computation phase happen, let's say, on a offline, right? So we get the results of that propagation, and we are not also orbital dynamic experts. So maybe you can also compute the propagation with some other toolings. So we created an interface and decoupled the rendering part and the visualization part from the computational part. And also Unity 3D offers quite a bunch of possibilities to explore that are far beyond just rendering a video like the one I presented to you today. So the opportunity is that, yes, we observe this kind of gap in the community. And we started to discuss with Alice, and we believe that a tool such as the one we wanted to create could be a unique opportunity to support network and protocol designers, engineers, with some intuition, right, on what the scenarios they're actually doing, right? And net protocol designers are not celestial or orbital mechanics experts. They don't have to do to be so, right? So the idea was to try to bridge that gap with IPN-V, which is what actually Alice started to work since then. And basically Alice evolved the prototype to it's a web app now that you can run online, and there is a demo I plan to make to you next, so I can show you how it works, even though the laptop is a bit laggy, but I will try. And the tool now evolved to something that is like fully interactive now. You can navigate in time and space there live. We have implemented some contact tracing. I think I will also elaborate a bit more in a few slides afterwards. And we are also, since we separated the computation part we can also now export contact plan formats for diverse DTN implementations around. This is a quick overview of the structure of the resulting IPN-V tool that I'm mentioning. So essentially, you have kind of a main controller there that operates the full tool. And then you have dedicated modules to compute basically the central element of the solar system. And we don't say sun, but star, because we are actually flexible to configure any star or any, let's say, potential solar system. And then we have the controller for planets. We have a controller dedicated to links because we really want to make focus on links there. We want to have the capabilities to implement like latency, visualization, and different stuff on the link level. And then the controller of the nodes that basically propagates landers together with the surface of the planet, or if they're orbiters around the other planets. And there's some other controls for camera and so on. And this is what I mentioned about the division between the computation and the visualization part. So the workflow with IPN-V is that we have first we compute with IPN-D. We call it the design part. This is a computation element there. But as I mentioned before, we can use our let's say very simplistic propagator calculation tool that we did at the beginning. But since we decouple it, you can also use SCK. You can use ORAKit, whatever you want. And to get that result or that file structure out, we created some JSON format there to define the scenarios in a very generic way, so that we can, in principle, generate that files with any tools that you have. And this was our way of just basically setting away from the multiple potential orbital propagators and so on, which are around the community. And basically, with this JSON file scenario, we just basically can plug them in or upload this to the web app. And we just basically visualize the scenarios we want to. This is basically the format of these JSON files are four JSON files format that we're using. We have one for a general configuration file that defines the scenario. So here we define the planets, the stars, the nodes, etc. We have of course a JSON file for the contact plan. So because we compute the contact plan offline as well. Computing the visibility, the line of sight in a time dynamic way is quite computationally expensive. So we do this beforehand as well. And this is why we can also export this JSON to ION format or HDTN or whatever format we want. And then we have a JSON for files for planets and nodes. This is where basically the X, Y, Z position in an heliocentric coordinate system is exported and is fed into the IPN-V. Quite some challenges that we needed to tackle to make the tool work was that Unity 3D and in general any game engine like Unity 3D, they typically work on float 32, right? These are like floating points which are designed to operate like in GPUs, like very, let's say, not super detailed or high resolution number. But when we work on a solar system scale, the space, the navigation space we need to use is not enough to cope with the float 32 structure. So we separated the visual 3D environment that is living on a float 32 for rendering purposes with, let's say, the real physical position module, which works on a float 64 there. We needed to implement origin shift because of even in that case, even if we move to float 64, rendering the resolution that you have close to zero with a floating point is far better than the one that you have farther away. And we have this type of issues when we are on the early versions. When we went to Pluto, you start to see some very weird effects like flicking and so on because of the inaccuracies of float. And the one way of overcoming that is to move the 0, 0, 0 origin point of your scenario to the planet that you're actually visualizing. So this is what we're doing now. And also we implemented some homemade ray tracing functions to compute the visibility and the links between the different assets. There are some performance evaluation I will skip quickly. I refer to your paper if you want to go there. There are some frame rates calculation around that. And we ran a quick demo in the 5 minutes I have left just to show how it works. So we took over one of the scenarios that Felix Lenge proposed some time ago as an example use case for the tool. This is we're talking about. We have 2 landers, 2 rovers on the moon, on Mars, 3 relay satellites, and 2 ground station there, standing for like what could be like NASA DSN. This is the numerical parameters for the reference, and let me see if I can just show you guys how this actually looks like. So this is the interesting. Why is I need to stop PowerPoint? I guess 1 second. Let me put this duplicate slideshow. Maybe this works now. Can I move away now? Yeah. So so we have, as I said, we have this WebGL tool now. It's like currently the user interface can have some improvement just for uploading the files and so on. So what I'm going to do is just going to upload here some files, which are the JSON files I just presented to you guys. So this is like documents here. I have some example. So you have the Mars communication scenario. This is a folder with the 4 JSON files that I presented to you. And I can upload this here. And this is what we get, right? So we have at the beginning like navigations with the numbers, so you can just place 1, you can go to Mercury or Sun, right? So just by pressing the numbers, you navigate to the specific planets on the solar system. So let's go first, for instance, to Earth here. And you can basically, of course, navigate with the cursor. We have here the 2 DSN nodes that were present in the scenario that I mentioned before. You can zoom in and zoom out. So we have here one of the DSN stations in Madrid and the other one in Australia. And then, of course, I will just speed this up a bit, hit play, and should start moving, I guess, or not. Let me see. So the time dimension here, there is a bar underneath that you can play with time there. Let me move to Mars and see if I can speed this up a bit. So it's moving, but it's very slowly moving. So, and these are the 3 orbiters and the 2 landers that we have on Mars. And these are the contacts ongoing with Earth. So if you basically position it here, we can see like the scenario moving with the real, as I said, these are realistic orbital trajectories computed with our own dynamic propagator that can, as I said before, we can use others if you want. We can plug these scenarios in and we are able to navigate and visualize here. For instance, let me just move over the zoom thingy here. You can see like a specific dates or a specific time how things are actually looking. Let me, maybe full screen will work a bit better. So here, so for instance, you can see the exact date where this is actually happening. So if you are, let's say, debugging some scenario, some contact plan, you can say, oh, I'm having some, I don't know what's the connectivity looks like at a given time, and then you can go, you can just navigate to the time, see how the topology is actually looking like, and you're gonna start to get some intuition of what's actually happening on the scenario you're using. Yeah, so the tool is there. If any one of you wants to play with it, I'm happy to give you some user and password there to use it. Maybe I can just don't want to take too much time here. There are a few menus here you can navigate, use to navigate throughout the scenario, and that's basically what the tools looks like. So let me go back here to my last slide. Yep, one more. Yeah, the laptop is a bit laggy. 1 second, let me. So what are we doing now, which are basically our next steps? So we are working on new export functions to integrate also other, particularly Godot, the ESA Godot propagation tool now. So to also get away from our simplistic propagation routines, and also start working on using the same web-based site to also start offering scenarios for people to play with. And you can get this scenario out and use the contact plans from those scenarios to have like a realistic database of a scenario to use on DTN. And also we are really moving away from Unity 3D to another game engine, which is named Godot, the same name that the ESA propagator tool, interestingly. And this is an open source also game engine that is unlicensed. Unity 3D is licensed in a very weird way because it's free to use until you make $1 million, I think, or something like that, and then you start to pay. But even though I don't think we get to the $1 million just yet. But this can be tricky for IPNC, and if we want to really use it on openly, it can become tricky. So we're starting moving away from that game engine. And something we're working with Alice as we speak is on visualizing DTN routes. Also quite a difficult thing to visualize, right, on IPN. So we're trying to highlight route path complete from multiple assets on the SSI. And also this is something I'm working at the moment, which is actually the contacts that you saw. As soon as there is line of sight, that contacts appears on the rendering scheme, right? But in fact, what we're working on is actually propagating the contacts at the speed of light, so that we can actually see the contact being created and terminated at the time it should terminate, so that the final bit of that bundle arrive at the destination by the time that the node is actually hiding in the horizon. And this will basically generate. I made some prototypes, and it's quite interesting to see how a contact is actually kind of a dashed line sometimes in the solar system scale, because basically the time that one bundle takes to arrive to the destination, the contact ended and started previously. So these type of intuitions are super interesting to see how these IPNs actually works. And something last to close, Unity 3 actually allows us to compile the same tool for a VR set. So we can basically plug like this type of helmets. Actually have one here because with D3TN we want to use it for a fair that we have at the end of the year. But possibly people that are around there can just put the helmet and navigate on the solar system there and play a little bit. So I think it can be a fun way of spreading the word as well of what we do with the IPN-SIG and IPN in general. So yes, that's basically it on my side. Yeah. So I guess again the stress is on so planning, education, and dissemination of IPN-SIG. This is the main idea here. The repository is available if you want to play with this. You want to build your own server with the IPN visualizer. You can get it from the repository. I have a few scenarios there for you if you want to play with. And that's it. I guess I'm just in time. So thank you very much.
Well, we do have time for questions. Wait.
Well done. That's not a question. It's well done.
The question was it well done?
Yeah, was
the
it
answer
well
was yes.
So, can you, like, if you had an existing model, say like ISS 3D model or something, could you incorporate it into that?
Yes, right. We can also incorporate easily the same model format that SDK is using. This is super easy to import. Actually, this is why SDK actually import them easily. And we can also add that to the tool. Yeah. I don't remember the format. It's a super standard one, but it's something you can export from Blender for sure. Yeah, it's something you can generate with Blender. Yeah.
Any other questions? All right. Thank you, sir.
Yep. Thank you, guys.